Right, so let's start with a knapsack problem, but now using backtracking. So we already know two kind of variations. One of them is fractional knapsack problem. In case of fractional knapsack problem, we can take the fraction of an item, and this particular problem is going to follow the greedy approach. The next type of knapsack problem that we have seen is 0-1 knapsack problem. And in this case, you can either select an article or you can reject it. So accordingly, I have the value as 1 and 0. So if you select an article, you just write down 1 corresponding to the index. If you do not select an article, you simply write down 0. And we have seen that this can be solved using dynamic programming approach. Now, knapsack problem using backtracking also has another name that is known as unbounded knapsack problem. So how it is different from the traditional knapsack problem is that whatever type of problem that we have seen earlier, in all the cases we have just one instance of an article, but here we consider that we have multiple variations, or we can say we have multiple articles of the same type. So let's say that the weight of article is 2 and let's say the profit is 10. So I can have multiple instances and you can take as much instances as possible. So if you just try to relate this, this is very much similar to the coin change problem that we have seen earlier. In case of coin change problem, again some amount will be given to you and some denominations will be given to you. And out of all these denominations, you have infinite supply of coins. Similarly, what we consider here that we have certain articles along with their weight and profit, but now we are not confined to just one instance, but we have multiple instances of the same type of article. So instead of going towards the algorithm, we'll just see that what is the difference among 0-1 knapsack problem and unbounded knapsack problem, right? So just see that how it is different in form of recursive formula. So in case of 0-1 knapsack problem, the thing was very simple. Just if I select an article, let's say I have selected a particular article I, then that article is now out of my reach, right? So when I'm selecting one article, next time there is no way of getting that article again. But when we talk about unbounded knapsack problem, then you can say that if a particular item is present, I can take multiple copies of it. So the input is now iterating on either n minus 1 if you reject an article, or it is going to iterate on n number of articles because you are going to have the multiple instances, right? So now the thing is that if we talk about the unbounded knapsack problem, then this kind of problem falls into the NP class. And one may argue that in case of dynamic approach, when we have tried to solve the 0-1 knapsack problem, then the total time, if you remember, was order of n into w. That is the number of articles we have along with the maximum weight that can be given for filling up the knapsack. So in that case, we have not concluded that the total time is polynomial. The reason is your total time is not only dependent upon the size of input, but it depends upon one more variable w, and w is something which is not related to the set of input. So in that case, we have seen that the total time is order of n into w, but we cannot say this as polynomial. Rather, such kind of problem is known as pseudo polynomial time, right? And this is also known as the weak form of NP class. So the knapsack problem actually has a pseudo polynomial time. It is not going to have the polynomial time solution, no matter which kind of approach you are going to follow. Even if you follow the greedy approach or you follow the dynamic programming approach, this everything boils down to the order of n into w, where w is the value which is going to represent the maximum capacity. So this is not in terms of input. Rather, n is something which is input, but w is not input. Therefore, I cannot say this to be a polynomial time. So this is actually going to take a weak form of non-polynomial time, right? So it falls into the NP problem. We are going to discuss about NP complete and NP hard in upcoming sessions. But remember that this knapsack problem, no matter which variation we are talking about, falls into the NP class problem, right? So I think the difference is clear that in case of 0-1 knapsack problem, we do not have multiple instances. So once you have discarded or selected one of the instance, next time you iterate on n minus 1 instances. But when we talk about unbounded knapsack problem, and if I have certain articles, so the limitations is that all the articles can be selected at multiple times. So there is No restriction on, let's say, selecting only one article, but we can select multiple article of the same type. Therefore, you can iterate on n number of elements. And if you reject the article, then you are left with n minus 1. So in case of 0, 1, either you select or reject. But in case of unbound, if you reject, that is fine. Because if you're rejecting, that means you are not including the particular article into the knapsack. So the choices are n minus 1. But if you are selecting an article, then you do not know that how many instances will take you to the final solution. So if you are selecting, you are again iterating on the same set of n articles. So this is the basic difference, and the way of solving the problem is again different. The reason is this is very much going to follow the approach of point change problem, but we will see that how this can be solved by using a tree structure. So consider an example here, right? So let's say that the capacity of knapsack is 8. It is followed by some 8 unit. You can say that, let's say 8 kg. Then you have 4 types of articles, and there are multiple instances of all these articles. Their weight and the corresponding value, or you can say the profit, is already given. What we need to do is we need to identify that if I have these much articles, then how I'm going to have the maximum profit such that the total cost will be lesser than or equal to 8. So this is what we already have. We have 4 kind of articles. We have multiple supply of all these articles. Their corresponding weight and profit is given, and the total weight of knapsack is 8. So what we are going to do is, in each and every node that we have created in the form of a tree is going to have 2 values. On the left hand side we have written weight, on the right hand side we have written the corresponding profit or value, right? So here you can see that although it is a little bit messy, but let's see what we have done here. We have started with 4 possible values. So I can either start with W1, or I can start with W2 or W3 or W4. The reason is all the values are lesser than or equal to the total weight of knapsack. So if I start with 2, I need to follow that what are the next possible values that I can take, including the same article again. Similarly, when I go to W2, you start with the first value, right? If you're selecting this, next time you will see that what are the multiple ways of getting the maximum profit with the same article again, right? So let's see what we have done. We have started with the 4 possibilities. I can either take W1, or I can take W2, W3, or W4. And if I take one particular article, I need to proceed further, because when I have taken W1, the total weight for this article is 2 and the corresponding profit is 4. So we are still remaining with the 6 unit of weight, and this 6 unit of weight can again be filled up in multiple ways. So we will start from left to right. We have selected the path W1. Now after W1, when I select this article, the total weight that I have taken is 2, and the total profit we have made till now is 4. Now after this, the remaining weight that I can put inside the knapsack is 6, right? So if the size of knapsack is 8 kg, we have already selected one article of, let's say, 2 kg. So remaining weight that I can fill inside the knapsack is 6 kg. So you can see that if the remaining is 6, what are the possibility of getting all the articles? So I can repeat the same article. So I can either select W1. The weight of the second article is 3 kg. So 3 is less than or equal to 6. Therefore, I can either select W2. Similarly, the weight of third article is 4. So I can select this weight, and the weight for fourth article is 6. So 6 is less than or equal to 6. So yes, I can select that article. Correspondingly, we have updated the weight. So you already have the first article of weight 2. If you select the first article again, then the weight that you have kept inside the knapsack is 4 and the profit made is 8. Similarly, if you put the second article inside the bag, so total weight will be 2 plus 3, that is 5, and total profit will be 5 plus 4, that is 9. Similarly, if you take the third article, then the weight of third article is 4, and 4 plus, previously we already have 2 kg. So 4 plus 2 will give you 6, and the total profit will be equal to 7 plus 4, that is 11. Similarly, for W4, we have taken 6 kg. because we already have the capacity of knapsack as 6. We have already taken 2 kg, so we still have 6 kg. So I can take the fourth article. So 2 plus 6 will give you 8, and the total profit will be equal to 8 plus 4, that is 12. Now you can see that from W4 I cannot go further. So I need to stop at this point. The reason is the capacity of knapsack and the number of articles that you have taken along with their weight are now same. So you have already filled the bag of 8 kg. I cannot move further. So after W4, I do not have any chance to explore further. Similarly, when we have selected W1 followed by W3, the total weight is 6. Although we are remaining with 2 kg, but this is something that we are going to explore after considering all these weights, right? So what we will do is, instead of starting from W4 to W1, let's move further in the left side of the branch. So I have taken 2 kg and the weight was 2. The total profit made was 4. Again, I can take W1. So total weight will be equal to 4 and total profit will be equal to 8. Now again at this point, I have possibility of obtaining some other articles. So can I repeat W1 here again? Yes, so I can repeat W1. Can I say that still I have some weight which is less than or equal to the weight of second article? So we already have 4 kg. I can afford 3 kg. So we have taken this and put it inside the knapsack. Similarly for W3, because we have already selected 4 kg. So this 4 kg can be selected. So we have taken W3. I cannot select W4 here. The reason is the weight for the fourth article is 6. The knapsack already contained 4 kg of content. So I cannot select 6 because 6 plus 4 will give you 10, which will be greater than or equal to 8. So I need to discard W4 at this point. Similarly, when we proceed, on the left hand side, you can see that we have selected 2 articles of W1. The total profit is 8 and the total weight is 4. Again, I can select W1. Now the total profit will be equal to 12 and the total weight will be equal to 6. Similarly, I go further. Here again we are selecting W1. So total weight is 8 and total profit is 16. Once you have reached from taking all the possibilities of W1, then we backtrack. So when we backtrack, we go back to the previous node in which we have taken 6 kg. So we have explored the path for W1. Now see that whether I can take second, third or fourth article. So clearly it is not possible. The reason is the weight for second, third and fourth article is 3, 4 and 6 respectively. But here when I take 3 or even if I take 4 kg or 6 kg, it will not be possible to fill the bag. So at this point I have just one option. Again you roll back. So when you roll back, you can see that the particular bag has 4 kg. So what are the possibilities of the different articles that we can explore? And why we are going in this pattern? We are going in this pattern so that when you return back to any particular node, and when you are selecting a weight, let's say Wi, then the only option that we are remaining with is Wi to Wi plus 1 up to Wn. So here when we have explored W1, we have seen all the possibilities of W1 with the remaining articles. So here when I take W2, I do not need to check for another W1 and so on. So here when you take W2, 4 plus 3 will give you 7 and total profit will be equal to 13. Similarly, I cannot take any other value now starting from Wi, that is W2, W3 and W4 cannot be taken. Identify the next possibility. I have 4 kg of weight inside the knapsack. Next 4 kg can be afforded here. So I can take the third article. 4 plus 4 will give you 8 and the total profit will be equal to 8 plus 7, that is 15. Then you roll back and identify the rest of the possibilities. So here you have 2 kg. I can take W2, W3, W4 and so on. We have seen that after W4, I do not have any possibility of getting a new article. But when I take W2, I need to identify that can I take a different article or the same article starting from W2 to Wn. So here I'm not supposed to explore W1. The reason is the combination of W1, W1 and W2 was already explored. So I do not need to repeat the same article because this will ultimately give you the same solution. So even if I take the first article followed by second and then first, or I can take first article, then first article and second. So this is not going to make any change in the total weight and the total profit, right? So here, whenever I'm reaching W2, I just find out the branches from W2 to WN. So here I can definitely take the second article of W2. Total weight will be equal to 5 plus 3, that is 8, and total profit will be equal to 9 plus 5, that is 14. After this, I cannot go further. Similarly, I cannot take W3 and W4. The reason is the remaining weight is 4 and 6. Similarly, we trace back. Now, when we have taken W3, I just see that can I take weight from W3 to WN? So after W3, I cannot take the second article W3. The reason is the weight here is 4 and 6 plus 4 will give you 10. Similarly, I cannot take W4. So there is no possibility of going further. Here we have taken W4 already. So the total weight is 8. Again, no possibility of exploring the further nodes. Then you trace back, do the same thing for W2, W3 and W4. So when you identify W2, make sure that you are identifying the next weight from W2 onwards. So do not see the possibility of W1 again starting from this node. So from W2 you have 3 and 5. Can I take the second W2? Yes, we can. So again the weight is 6 and the profit is 10. Now can I repeat W2 here? No, the reason is 6 plus 3 will give you 9, which is greater than 8. So I cannot pick that particular article. Therefore, no possibility of identifying the next values. Similarly, when you trace back, identify whether I can take W3. So here you can take W3. 3 plus 4 will give you 7 and 5 plus 7 will give you 12. Again, there is no possibility of taking W3, W4 and so on. So you trace back to the initial node. Start the same sequence for W3. We have taken 4 and 7. Can I repeat W3? Yes, I can repeat W3. The total weight will be equal to 8 and the profit will be equal to 14. Now, can I take W4 here? No, I cannot take W4 because 6 plus 4 will give you 10, right? And similarly, when the knapsack is full, I cannot add any other article. So you trace back and go to the initial node. Now, can I take W4? Yes, I can take W4. The total weight is 6 and the corresponding profit is 8. Now I need to explore that can I take the second article of W4 here? So the answer is no. The reason is 6 plus 6 will give you 12, which is definitely greater than 8. So I cannot explore this path. So whatever tree you are getting is actually all the possible combinations of weights that we can take. And this is not required to be in sequence. The reason is if I have a bag and if I have multiple instances of different articles, I can take one article 2 times in any sequence. It is not going to make any change. Therefore, we have not explored all the remaining path. If you want to explore the remaining path, that is perfectly fine, but you will not get a different set of answer. That's why we have created a graph in such a way. So when you create this particular nodes, you can see that all the leaf nodes will give you the final possibility of answers. And out of these final possibility, we need to identify that in which case we are getting the maximum profit, right? So what are the nodes I need to check? I need to check this node with 8 and 16, then 7, 13, then 8, 15, 8, 14, 6, 11, 8, 12, 6, 10, 7, 12, 8, 14, and 6, 8. Now you need to identify that in which of the following leaf node I'm getting the maximum profit. So the maximum profit I'm getting is from this particular path where we have taken 4 instances of first article, and therefore the total profit that we can make out of unbounded knapsack problem is 16 by selecting 4 article of first weight.